Okay, this video starts our second week of Unit 5 in Calculus. And in it we're going to practice some more with our integration as well as sigma notation. Now in this first example we're talking about the graph of a sine curve, and before we get too far let's just remind ourselves of what that looks like. Remember, the sine function starts at the origin, and to the right one key data point we would go up one data point and then down to the middle, and then as we continue we can regenerate the sine curve. And so it looks something like this as we move to the right. Now these key data points are pretty important for us to recognize. You should recall that this x value is pi over 2 and we have a y value of 1. Then we have an x value of pi, then of course 3 pi over 2, and then finally 2 pi before the period or cycle ends, and the y value decreases down to -1. In this example we're talking about the region R that's being bounded by the graph f of x equals sine of x, so we just sketched that. So between that graph and the x-axis, in between x equals 0 and pi over 2. So between x equals 0 and x equals pi over 2, the region bounded by the graph and the x-axis is right here. So that's the region of the graph that we're talking about. And as we continue to read this problem, we're being told that we're going to create Riemann sums with 6 subintervals. So this particular sketch probably won't do. I need 6 subintervals, not just 3. So I'm going to recreate that graph, this time with spacing for 6 subintervals rather than just 3. And I think it'll fit right here. Okay, so I think this scaling would be appropriate. We've got room for 6 subintervals along the x-axis, and I went ahead and placed 2 subintervals on the y-axis. As far as our scaling goes, the y values extend to +1, and the x values extend out to pi over 2, and of course they started at 0. Now half of pi over 2 is pi over 4. And I think that would be sufficient to label the x-axis, although you could indicate the subintervals a little bit more clearly. We have pi over 12, and then 2 pi over 12, which reduces to pi over 6. Here's 3 pi over 12, 4 pi over 12, which is pi over 3, and then 5 pi over 12 and 6 pi over 12, which reduces to pi over 2. When sine is evaluated at an x value of 0, we get a y value of 0, and when sine is evaluated at pi over 2, we get a y value of 1. When sine is evaluated at pi over 6, this is something we should remember from our unit circle. We get a y value of 1/2. When sine is evaluated at pi over 4, well, we get radical 2 over 2, and you may remember that decimal equivalent. That's approximately 0.707. So if I were to plot that, 0.7, I don't know, I'd say right about here. It's a little bit less than 0.75. And then sine evaluated at pi over 3, we know is radical 3 over 2, which is approximately 0.866. So with the y value here at 0.866, that might be a data point, I don't know, right about here. So these are 5 data points that we should be familiar with based on our unit circle, and that does allow us to create this sketch with a fair amount of accuracy. This point might have been a little bit high here because I want a smooth and a continuous line that connects these points. That looks representative. It may not be perfect, but I think it does a fair job representing the sketch. So now for the task at hand. We are looking at creating a left-hand Riemann sum. Now, in the last few videos I didn't name these as such. And the mathematician Bernard Riemann is the one that gets credit for this particular process, creating these subintervals with evenly spaced partitions. And a lot of times we just end up using rectangles, but trapezoids and other geometric shapes can be used as well. So when we say a left-hand sum, we're really talking about a left Riemann sum with 6 subintervals. Well, we've already established these subintervals. That's 1 here, 2, 3, and so on. So we've got these 6 sections. And you'll notice, though, there were technically 7 values used to establish these 6 intervals. So we have a value at the very beginning and at the very end, and all of these subdivisions in between, and that's what made our 6 subintervals. Now, if we're focusing on what we call the left-hand sum, well, then we want all of the left-hand sides of these subdivisions to dictate the height of our rectangle. And so that would be all of the x values from 0 in this case up to 5 pi over 12. And when we switch to our right-hand sum, well, we look at the right side of each of these subdivisions and use all of those x values to compute our y values, our heights of the rectangles. And so the average of the left-hand sum and the right-hand sum tends to give us a pretty good approximation for the area underneath the curve. In general terms, we might express a result kind of like this. For A, if we're talking about a left-hand Riemann sum, usually we just call these LHS for left-hand sum, that would be the width of each subinterval, so I'm going to call that change in x, times all of the y values starting at element 0 up to the second to last element, and we'll call that y sub n minus 1. So if this was considered the first x element, the initial x element, we usually call that x sub 0. Then we've got x1, x2, x sub 3, and so on. By starting at 0, by the way, then when we get to the end here, we see x sub 6, and that indicates, again, our 6 subintervals. Starting at 0, that accounts for that extra component needed to make these 6 subintervals. This last position at the end is always equal to the number of subdivisions that you've got. For our right-hand sum, on the other hand, the right-hand sum, well, it's still delta x. The width of the rectangles are all the same, but this time we're starting at the height of the rectangle at data point 1, and we're going all the way up to the height at data point 6, or n, the last one in the interval. And we talked a little bit about this in class on Monday of last week. So delta x, it's essentially been factored out of the sum of all of these areas because delta x is consistent. So if I were to sketch this left-hand sum with a series of rectangles, it would look something like this. The first rectangle has a height of 0, and the second rectangle, again, I'm looking at the left-hand interval of the, or left-hand side of the interval here. There's our left-hand rectangle, another left-hand rectangle, and so on. So within these subdivisions, we've got all of these rectangles, and the heights of each of these rectangles are, again, developed by the y values on the left-hand side. So y0, y1, y2, 3, 4, and then ultimately y5. Now, some of the heights are easy to identify, and as well as the delta x. The delta x in this case, the width of each of these intervals is pi over 12. The first y value was 0, but I don't have the second y value memorized, so I'm going to need a calculator for that, but it would be whatever the sine result is at pi over 12. The third y value, or the third height of the rectangle, is 1/2. Then radical 2 over 2, then radical 3 over 2, and then lastly, the final height, well, subinterval number 6 is based on the height at 5 pi over 12, and I don't think I've ever memorized that one, so I'll rely on a calculator to evaluate it. So whatever sine of 5 pi over 12 is. And if I reach for a calculator off screen, I end up with an area of 0.8634. And so based on our left-hand sums, we're going to estimate that the area underneath this curve is 0.834. But hopefully you're not satisfied with that, because you'll notice right away that all of these sections, all of these rectangles ended up being shorter than the curve itself, and each of these gray marks represent regions that were underestimated. And so we would most likely say that this calculated result, this area here, is an underestimate for what fits underneath that curve. Now, of course, one way to fix that is to try a right-hand sum and see what we get. Well, again, we still have the same subintervals, the 6 subintervals, but this time we're building the heights of the rectangles based on the right-hand data points. So the height of this first rectangle is now here, and then the second rectangle, the third, fourth. Now all of these intervals or subintervals create their own rectangles, and rather than being an underestimate in each of the cases, we have a bit of an overestimate, because the height of this blue rectangle is now taller than the curve. Now, it would be nice if the overestimate for this rectangle was exactly the same as the underestimate for this rectangle, but that's clearly not the case, because this diagonal is not perfectly bisecting that resulting rectangle. So they're not going to cancel out perfectly in a curve, but the areas are going to be pretty close, pretty similar to one another. So let's see how this right-hand sum computes. The delta x, the width of each rectangle, is again pi over 12, but this time we're starting with the first y value, not at the initial y value, but the second y value labeled as y1, and that was this guy here. So we're going to reuse sine of pi over 12, and then a half, then radical 2 over 2, radical 3 over 3, radical 3 over 2, then the y result for sine of 5 pi over 12, and then lastly, so we're essentially reusing these data points again, but lastly we end up with the very final y value, which was 1. So again, this time the heights of the rectangles were determined on the right-hand side. So we got y1, y2, 3, 4, 5, and 6 instead of 0 up to 5. Now when I reach for a calculator off screen and compute this result, I end up with 1.1252. And if I add these two together and divide by 2, that's going to generate the average. So out of curiosity, the average calculates out to 0.9943. So that's pretty interesting. Our underestimate was 0.86. The overestimate was 1.12. The average came out to 0.9943. And as it turns out, the actual area, does anybody want to take a guess? The actual area is precisely 1. And we discussed this a little bit in class last week. We can obtain the actual area because we have the function that describes this curve and we have the boundaries. We can actually use a definite integral to compute this result. Now we haven't practiced these just yet, but as a preview, from an x value from 0 up to pi over 2 of the function sine of x with respect to x, if I were to use a calculator, or if I would use my calculus skills that I learned a little bit later this week, the evaluated result for this definite integral is precisely 1, and the area under that curve, with no estimating at all, the precise area is exactly 1. And as it turns out, the approximation here, the underestimate and the overestimate, ended up averaging pretty nicely. Now, we don't always have the function that describes the particular shape. Sometimes we're measuring data points over time, and we estimate the curve that fits that data, and we don't have the equation that makes it. In this case, for example, we don't know the equation that made this curve, but we could still utilize integration in order to determine or estimate the area under that curve. So in this example, we're told to approximate the area of the region bounded by the graph as we've shown here. It's kind of this greenish color. And we're looking at the region between 0 and 6 on the x-axis, and we're separating this into 3 subintervals. We're going to use left and right-hand sums to obtain these approximations. So between 0 and 6, we have to have 3 subdivisions. So those occur at 0, 2, 4, and 6. So again, we would call this guy x0, x sub 1, x sub 2, and x sub 3 for our 3 subintervals. And then we've got y-coordinates. So this y-coordinate here I would call y0. The y-coordinate here I would call y1. The y-coordinate at 4, y2. And then the y-coordinate at 6 I would call y3. So now we've got x-coordinates and y-coordinates at each of these edges or endpoints of the subintervals. So for our left-hand sums, we'll choose the height based on the left-hand side of each subinterval. So that would be the height at y0, y1, and y2. So as I'm labeling the left-hand sum, I would say the delta x times y0 up to y sub n minus 1. So in this case, delta x is 2 units, y0 was 1, y1 was 6, and y2 was 9. And 2 times 16 is 32. So the left-hand sum produces a calculated result of 32. And I'm guessing that this is going to be an underestimate because the height of each of these rectangles in these regions is below the graph itself. So I'm guessing that 32 is an underestimate. The left-hand sum is not always going to be an underestimate. It just happens to be so in many of the examples we've seen so far. Especially if we consider a function that's decreasing, the left-hand sum would indicate an overestimate. But in most of the examples we've seen so far, the functions have been largely increasing, and that's why this left-hand sum has been an underestimate. Now for our right-hand sum, the setup looks similar. Instead of starting at y0, we're starting at y1, and instead of ending at the second to last element, we are ending on the last element. So the delta x, or change in x, is still 2 units. The height ends up being 6 plus 9 plus 11 this time. And this area result comes out to be 52. See, that's 26 times 2. Yeah, 52. If we were to average these two, the average comes out to be 42. And so an interesting point that we might consider, and a slight change to the Riemann sums, the left and right Riemann sums. Let's just point something out here. In the blue rectangle, we had a large underestimate, and in the green rectangle, we had a large overestimate. And the fact that we averaged the two results negated a lot of those errors. But another option that we have is to create the height of our rectangle not based on the left endpoint or the right endpoint, but the data point exactly in the center. Let me show you what I mean by that. I'm going to erase these rectangles here. What if, instead of using the height at 0 or 2, what if we used the height at 4, or the height at 3, or the height at 5? This time, when we generate rectangles based on those positions, then built within the rectangle itself, we have both an over and an under estimate. This rectangle overestimates on this portion, but then it underestimates in this portion. It overestimates here and underestimates there, and then it overestimates Little bit of an overestimation right here because of the dip in the graph, but then it underestimates over here. We would call this a midpoint sum because we are determining the height of these rectangles, the height of these geometric shapes, based on the midpoint value. So again, the midpoint sum, we might say MPS. The width of the midpoint sum is still 2, right? Each of these rectangles had a width of 2, but this time the heights are a little bit different. We have a height of 4, a height of 7, and a height of 10. 4, 7 is 11, and 10 makes 21. 21 times 2, well, that's kind of interesting. The midpoint sum calculates out to be 42 units. We were able to obtain the result 42 with one single calculation, whereas over here we needed 2 calculations and then the average to obtain the exact same result. Now, this will take a little bit more investigation, but I think this is a coincidence that they're the same. I don't think it's always going to be that way. Because when we average 2 rectangles, that generally produces a trapezoid area. And so if we had built a trapezoid based on these endpoints, the area of the trapezoid would always be the average of the 2 rectangles, I believe. I think we just got lucky here that the midpoint sum was exactly the same. But I'll have to look into that. Maybe we can discuss that in class at another time. Let's take a look at another example. This time we're being told that a car comes to a stop after 6 seconds and the brakes are applied, and that's what's bringing this car to a stop. We were able to record the velocity at different positions, right? So at 0, 2, 4, and 6 seconds, we knew the velocity of the vehicle. Maybe the computer returned that result to us. We would like to know the distance that was traveled over that amount of time. So evidently our odometer was broken or not accurate enough, but we were able to determine the velocity at each of these positions. So let's see if we can calculate the distance traveled based on an approximate integral. Now, using the table, we can create a left-hand sum with these 3 data points, and we can create a right-hand sum with these 3 data points. We don't even need a sketch, although Part B does ask us to produce a sketch before we're done. Let's go ahead and generate the results for the left-hand sum and the right-hand sum without the sketch, and then we'll see how that compares to the image. So the left-hand sum, we can use 1, 2, 3 of the 4 elements, and so it looks like our delta x, the width in the x values, is 2, and that's consistent, so that's nice to see. So we've got a width of 2 times a y value of 0, 2, y value of 88, 45, and 16. For the right-hand sum, the width again is 2, only this time we're looking at 1, 2, these 3 y values. So the y values are 45, 16, and 0. Now, as a point here, I want to indicate that 2 being our width contained a unit of seconds. So 2 seconds in width, and 88 plus 45 plus 16. That's a sum of velocities. So those are units of feet per second. When I multiply seconds times feet per second, my resulting unit will be feet, and the actual value, the result of this computation is 298. So one estimate based on the left-hand data points is that we've traveled 298 feet. In the second example, we again obtain feet as our unit. Seconds times feet per second reduces to feet, and this calculated result is 122. Now, we really had to use a left-hand sum and a right-hand sum here because we only had a handful of data points. If I wanted to use a midpoint sum like we had established in the last example, it would have been necessary for me to identify essentially the velocity at time 1, 3, and 5, and we just didn't have that information provided to us. So the left-hand sum in this case was an overestimate, I'm guessing, and the right-hand sum, again, I'm guessing, is an underestimate, but we can average these two, and the average comes out to be 210 feet. So if these velocities were reported correctly over those 4 data points, it appears that we've traveled 210 feet in that amount of time. And as far as a sketch goes, if we had an x and a y axis, the labels might go like this, and we can plot our data points, 88, 45, 16, and 0. And if we were to connect these data points with a smooth curve, which would essentially mimic the behavior of that car as it's coming to a stop, we would then, of course, recognize that our left-hand sums were overestimates in this case. So a left-hand sum rectangle was drawn here, a left-hand rectangle was drawn here and here. So each of those had an overestimate, whereas our right-hand sums in this case, from the right side of that interval, produced the lower or underestimates that time. And so the next example in this video is one of a midpoint sum. So I'd like for you to try this one on your own. Can you use the information provided, and this time we do have an equation, can you establish the heights of the rectangles necessary for the midpoints and then calculate their sum, or the sum of the areas? Please do so. Pause the video now and resume playback in a moment to check your work. And so as a reminder, the midpoint sum uses a delta x times a series of y values. And what I've noted here is that the y values occur at basically half intervals, not whole number or integer intervals, but half intervals. So if you recall, we called this position x0, x1, x2, 3, 4, and 5. For our 5 subintervals, that was indicated here. And for the left-hand sums, we would have used these 5 positions. For our right-hand sums, we would have used these 5 positions. But for our midpoints, those occur exactly in the center. So that's why I called this the 1/2 position, or the 3/2 position, and so on. So the location of these with regards to the subintervals are landing in between these nice integer subscripts. And the y values that are computed, again, can be computed by the appropriate x values. So even though we're calling this x sub 1/2, that did have an x value of 1, and this was an x value of 3, 5, 7, and 9. With those x values, we were able to compute the y results, and the sum of those heights multiplied by the width of each interval produced an area of 670. And by way of comparison, the left-hand sum using 5 subintervals was 760, the right-hand sum was 560, and that produced an average of 660. So again, a slight difference here, which I think supports my notion that the midpoint sum is definitely not just the average of the left and the right-hand sums, but it is pretty close. The results are pretty close here. And if I were to use precise integration using techniques from later this week, we would integrate from 0 to 10 along the x-axis of the function 100 minus x squared with respect to x. And this result comes out to be 666.6 repeating. So this is kind of an interesting result because our midpoint sum was 670, our average of our left and right hand sums was 660, and if I were to average those two, we would have 665, and that's awfully close to the actual precise area. So depending on the level of precision that you would need, sometimes estimates would be sufficient. Perhaps averaging multiple different estimates might be pretty good. But the alternative, of course, the precise result, we can't really beat that, but we don't always have this function to utilize. So that's our holdup there. To finish up this video, I'd like to just real quickly talk about sigma notation. You're going to see these in Math Excel, and I think their help tools do a pretty good job of explaining a process to complete them. But I would just like to remind you of my interpretation and what I think about when I see them. So I would encourage you to try all 4 of these problems, even though I'm not going to walk through each one in this group. But essentially, the sigma does remind us that we need to add together a bunch of results, and in this case, we're going to be adding k squared values for k values that exist between 1 and 4. So this sigma notation here for part C is really telling us to take k squared from 1 up to 4 and add all of the results together. And in this case, the total is 30. So the result for this sigma calculation is 30. For part D, we're taking 1 plus n squared. So 1 plus n squared for n values between 1 and 5. So 1 plus 1 squared plus 1 plus 2 squared, and so on, all the way up to 1 plus 5 squared. And I believe this result comes out to be 60. So the summation notation here leads us to a result of 60. And so I think you should be able to handle A and B on your own. Try those and then see me if you have any questions. And then lastly, we're given a pattern of values that are being added together. So it would be nice if we can condense this pattern into some sort of sigma notation. And I'd like for you to try to do so. I'll complete part A here, but I'll let you try B and C on your own. And what's interesting is that the answers may not be unique. There may be more than one result to each of these problems. So pause the video and think about what sort of pattern would be necessary to add these numbers together, 1, 3, 5, 7, basically all of the odds. What would that pattern look like, and how could you report that in sigma notation? Take a moment now to try this and resume playback in a moment to check your work. Well, for me, I saw this as the summation from 1 to 50 of 2n minus 1. 2 times 1 minus 1 is 1. 2 times 2 minus 1 is 3. 2 times 3, the next number in the list, 2 times 3 minus 1 is 5, and so on. And so this summation would work for part A. Another one that would also work is this summation. What if we said from n equals 0 up to 49? Then couldn't we say 2n plus 1? Because 2 times 0 plus 1, well, that gives me 1. 2 times 1 plus 1 is 3, and then 5, and so on. And then ultimately up to 2 times 49 plus 1, that lands us at 99. So this summation notation works as well. And that's part of the reason why we say that our answers may not be unique. So as you try B and C on your own and come up with solutions, if you're not quite confident in your answers, then please let me know, and we'll chat about them in class or through email. Thanks for watching.